Okay, we're moving into rationalizing denominators. So in the nicest case, well, I guess rationalizing denominators, probably should explain what that's happening. So we want to get rid of square roots in the denominator. Usually it's kind of hard to do a lot of things that we can do in mathematics with a square root existing or a cube root or something like that in the numerator. Whereas if I have something in the numerator and let's say just dividing by 4 or something, then I know I can kind of split it into a certain amount of units. So when we have a square root on the bottom of our denominator, to resolve that, we can multiply it by the exact same thing. So if it's just a single root, I can multiply it by itself, and that will make it so that I have 5 root 3, and so the bottom will become, well, it'll become square root of 9, and square root of 9 is 3, and I stop. So it's fine having a radical in the numerator, less so in the denominator, and that's kind of the name of the game in this section. If we can avoid it so that, or we can avoid radicals in the denominator, then we are good to go. Now for this problem, I have a root 4x in my denominator, so I multiply it by root 4x, and then if I multiply the bottom by something, multiply the top by the same thing. And so I will get 4x in my denominator, and then 25 times 4x gets me 100x. Now, we might run into the case that we can simplify a little bit further. In the first example, we can simplify our root. It's the square root of 3. We're kind of done. In this case, 100, we can take the square root of that. It's 10. So I could take the square root of 100 is 10. 10 times 3 gets me 30. And then I have the square root of x still on the inside of my fraction. And now always, 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 if we can reduce, we should reduce our fraction. And 30 over 4 does reduce. Those are both even numbers. So 30 divided by 2 is 15. 4 divided by 2 is 2. And now I'm left with 15 root x over 2x. Now with the cube root, it's a very similar concept, except for just multiplying it by itself once isn't going to do the job. I need to do that 3 times. So I have, well, 2 additional times, I suppose. And so if I have a cube root of an entire fraction and I want to rationalize the denominator, well, I break it up into 2 separate roots. And instead of just multiplying the top and the bottom by the cube root of 9 once, I just have to do it twice because I want that kind of 3 of a kind thing going on. So if I multiply everything out, the cube root of 9 times 9 times 9, it gets me just 9. That was the entire purpose of it. I believe it's something like 279. Not super important. The whole thing is that the whole purpose is that I was able to undo that cube root in the bottom. And then the top is 9 times 9 is 81, times 2 gets me 162. And now I have to simplify the cube root of 162, which I do off to the side here because I ran out of space probably. So 162, I can break that into 2 and 81, which I can break into 9 and 9, which I can break into 3 and 3, and 3 and 3, and very poorly animate the fact that I have 3 of a kind of 3s, and then I have a 2 and a 3 left over. So I can pull a 3 in front of my cube root, leave behind a 2 times 3 gets me 6. And then 3 divided by 9 does simplify. 3 fits into both of those numbers, so it would reduce to 1/3. And instead of kind of leaving that 1 in front of our cube root of 6, we just, he's there, he's just invisible, so we just leave it as the cube root of 6 over 3. Now, if we have variables in our denominator, it seems like we would have a different process, but we don't. I guess in this case, I simplified first, but you don't have to simplify first. Just makes the problem much more wieldy. So 2 options you can do, like we did on the previous slide. I could multiply the top and the bottom by cube root of 27 2 additional times and then simplify from there. Or if we see up front that I can simplify things, that tends to make my life a little bit easier. So here I have the cube root of 27x to the 4th. Cube root of 27 is 3, so I can pull that number out. And then I have x to the 4th, so the cube root of x to the 4th, I have one group of 3s, or sorry, 3 x's, and then 1 x left over. So I pull that x out and put it in front. And now is where I can kind of say, okay, I still have my cube root in the bottom. I'm going to have to multiply the top and bottom by cube root of x 2 more times. So that leaves me with, I can combine my x's on the top, so I'm left with z squared times x, or z squared times x squared. And then for some reason in this case, I multiplied the x's in the denominator. Cube root of x times cube root of x times cube root of x is the cube root of x cubed, which just the cube root of x cubed is x. And so I could have really just honestly skipped that step. And that leaves me with my final answer. I can't simplify any further because there's a number on bottom, there's nothing on top. I can't simplify the cube root on top any further because I only have 2 z's and 2 x's. So that's it. That's my final answer. Now, something that, was this earlier in this one, or I recorded a lot of lectures tonight, so maybe this was on a previous lecture, but I talked about a problem where we had the difference of squares. And so when we're factoring, there's a really nice property that happens if we have the first term is something nice squared, the second term is something nice squared, and there's a minus in the middle. And so why that's such a nice thing is anytime that happens, we can actually just take the square root of both of those terms, slap a plus between them for my first factor, slap a minus between them for my second factor, and I'm done. I don't have to do the whole game of, okay, what multiplies to C and adds to B and figure all of that out. That's always the breakdown. Yes, it's got to be kind of particular. I have to have 2 nice squared terms and I have to have a minus in the middle, but we see this a lot in mathematics, so it is kind of one of the few processes that I recommend just straight up memorizing. So when you see it, you can just say, great, my answer is right here. I don't have to do any math. Now, the reason why I bring that up here is because it provides an example of a conjugate. And so a conjugate is if I have 2 terms, then I just take whatever is in between those terms and I flip the sign. So the conjugate of x plus 2 is x minus 2. The conjugate of x plus y is x minus y. The conjugate in this case, we typically try and tie to the actual roots if we can. So here I have root 3 plus 6. I'm going to flip the sign in front of my root 3 and get negative root 3 plus 6. So that's what we deal with when we're dealing with conjugates of roots. Instead of just what's in the middle, we take the sign of whatever's in front of the root and flip it. Okay, so now we're going to use conjugates to rationalize the denominator. So that's the whole purpose of that last slide, is to make it so that we know how to use conjugates in this type of rationalizing a denominator. And honestly, this is the most frequently how we see rationalizing the denominator. We don't usually see it in like the single terms that we saw in the previous couple of slides. And so the whole reason that we talked about it is, yeah, let's go back to this. So in the forward directions, yes, I'm factoring it and I get that x plus 2 times x minus 2. But now in the reverse direction, what I'm going to try to do is I'm going to, if I multiply those 2 binomials, I get both of those things being squared, right? I have x plus 2 times x minus 2. And so if I multiply those things out, I'm going to get x squared minus 4, x squared and 2 squared. And so that's what we're going to use here, is I want to get rid of that root 5, and it's not going to work if I just multiply by a straight root 5, because yes, the bottom left term will be regular 5. The bottom right term will become 3 root 5, which doesn't get rid of my root at all. Where instead, if we multiply by my conjugate, then what happens is I can use that formula previously to say that, okay, well, that's a difference of squares. That means my first term is going to be squared, and I'm going to subtract my second term being squared, which root 5 squared is 5, 3 squared is 9, and so that's how my denominator became 5 minus 9. All of that being said, if you want to, and I do highly recommend this if this is the first time you've seen rationalizing the denominator, if you want to multiply it out, you're going to see that you get that root 5 times root 5, which is 5, and then a minus 3 root 5 and a plus 3 root 5, which will cancel themselves out. And then negative 3 times 3 is negative 9. So this is one of those cases, those rare cases where I feel like you should maybe just blindly memorize the formula because it saves you such a headache. But if you don't get where that comes from, don't fall on it, or don't just always use it and not really get why you're using it. Instead, just go ahead and multiply them out. That's better than blindly following it and not getting why. Okay, so then I subtract 5 minus 9, I get -4. And then, well, okay, I can multiply out my 4. I would get 4 root 5 plus 4 times 3. Well, if I divide both of those things by -4, I get negative root 5 minus 3. Or another way to think about it, 4 divided by -4 is -1, and then I distribute and I get negative on both of those. Now, I have a little bit more of a complex case, but the concept's still the same. I have 2 root x plus root y. I'm going to multiply the top and the bottom by the conjugate of the denominator. That's the only part I care about. So the conjugate of that is 2 root x minus root y. And again, if you want to use the formula, great. I think I do it out step by step here. No, I do not. I just write it out. And so really all I did in that step, which wasn't the most helpful, is I just made it a single fraction. But essentially all you're doing is you're taking 3 root x, you're multiplying it by the numerator on the top right, 2 root x minus root y. And so now if I FOIL that out, and if I use the formula on the bottom, I'm left with 2 root x squared, which is 4x, minus square root of y squared, which is y. And then my top doesn't simplify a whole lot. Sure, the first thing kind of comes out pretty nicely. 3 root x times 2 root x is 3 times 2 is 6. Root x times root x is x, minus 3 root xy. And that's my final answer.